Welcome to The Explainer. Today we're diving deep into the brain of automation itself, the Programmable Logic Controller, or PLC. You know, it's that unsung hero running everything from giant car factories to the power grid.
Okay, so how does this industrial brain actually work? How does it think and act? Well, it all boils down to a fundamental blueprint, this core architecture that, believe it or not, every single PLC system is built on. Let's jump in.
All right, so here's the thing. Every single PLC, I don't care if it's brand new, 20 years old, big or small, they all follow this same standard block diagram. If you get this, you get how they all work. It's the key.
And here it is. This is the whole shebang. You've got four main players on the team. The power supply, which provides all the juice. The input modules, which are basically the system senses. The CPU, which is the brain. And the output modules, which are the muscles that get things done. So let's meet the team.
Okay, let's really break this down. We're going to look at each piece one by one, because once you understand what each part does, the whole system just clicks.
First up, you've got the power supply. Super straightforward, right? It's literally the heart of the system, pumping power into everything else, the CPU, the modules, all of it. Sometimes it's a separate unit you clip on, other times it's just built right into the main CPU block.
Okay, next up, the input modules. The best way to think about these, they're the PLC's senses, its eyes, its ears. They're constantly listening to the outside world. So when an operator pushes a button or a sensor sees a box on a conveyor belt, this module grabs that signal and turns it into ones and zeros that the brain can actually understand.
And right in the middle of everything, you have the CPU, the brain. This is where the magic happens. It's where the program you wrote is stored, and it's constantly running your logic, making all the big decisions based on what it senses the input modules are telling it.
Now, inside that CPU, the memory is kind of split in two. You've got one chunk that's reserved for the manufacturer. Think of it like the PLC's operating system. You can't touch that. But the other part, that's the user memory. That's your space. It's where you load your program, your logic, all your data.
So, the brain makes a decision. What happens next? It has to do something, right? Well, that's where the output modules come in. If the inputs are the senses, the outputs are the hands and the muscles. They take the commands from the CPU and make things happen in the real world. Firing up a motor, turning on a warning light, opening a valve, you name it.
Okay, pause for a second, because this is super important. It's a classic mistake. The PLC's outputs are, well, they're not built for heavy lifting. They're low power. You never connect something like a big motor directly to a PLC output. No way. You'll fry it. Instead, you use the PLC to switch on a small relay or a big contactor, and that device handles the heavy-duty power. It's like a buffer that protects the brain.
And how does it protect itself? Well, through this really clever trick called optical isolation. Basically, there's no physical electrical connection between the high-power world of the factory floor and the delicate, sensitive CPU. The signal is transmitted across a tiny gap using light, like a little LED blinking at a sensor. It's genius! It means if there's a huge electrical surge out on a motor, it can't jump that gap and obliterate the PLC's brain.
And finally, we have the programming device. This is your laptop, your computer. It's where you become the teacher, telling the brain what to do. But here's the really cool part, and it gets to the heart of what a PLC is. Back in the day, you'd have to physically wire up huge panels of relays to create this logic. Now, you just draw it. The very same control circuits that engineers used to sketch out on paper, well, they're now drawn using the same symbols on the same kinds of software programs. You're essentially drawing the circuit, and then you just download that drawing straight to the PLC's brain.
Okay, so that's the blueprint, the theory. But what do these things actually look like when you open up a control cabinet in a factory? Let's take a look at how that block diagram turns into actual physical hardware. When you get down to it, PLCs really come in two main styles, two different design philosophies. On one hand, you've got the all-in-one compact PLC, and on the other, you have the custom-built, almost Lego-like, modular PLC.
Let's start with the compact PLC. Something like this Siemens S7-1200 is a perfect example. It's exactly what it sounds like. Everything you need is packed into one single box. The brain, the power, a fixed number of inputs and outputs. It's all in there. These are awesome for smaller, simpler jobs.
But then you have the modular PLC, and this is all about flexibility and power. Here, every single component we talked about, the power supply, the CPU, the I/O, is its own separate module. You literally click them onto a backbone, which is called a rack. This lets you build a totally custom controller for really big, complex systems.
So let's take a closer look at these modular systems, because once you see how these blocks fit together, you really understand why they are so powerful and why they're used for the biggest, most complex jobs out there.
A modular setup is all about having the right tool for the job. You've got your basic signal modules for your standard digital and analog I/O. Then you've got things like interface modules, which let you connect multiple racks together. You've got communications processors for networking, and even specialized function modules for really tricky stuff like high-speed counting or complex control loops. So you take one of these racks, right, the metal backbone of the system. You can typically slide in up to 8 of these different modules, and that's not even counting the CPU and power supply, which have their own spots.
But what happens if 8 modules isn't enough? What if you have a massive machine? Well, that's where those interface modules come into play. They act like bridges, letting you connect up to 4 of these racks end-to-end, all reporting back to that single CPU.
And right there, that's the beauty of modular systems. You do the math, 4 racks with 8 modules each, that's 32 modules total. A single CPU can control this whole massive array, managing a huge number of signals and tasks. It's how you scale up for the really big jobs.
So what's the big takeaway here? It's that all PLCs, at their heart, share that same block diagram structure. They'll either be a compact, all-in-one box or a custom-built modular rack. Once you understand that fundamental idea, you can walk up to almost any control panel, look inside, and have a really good idea of what you're looking at and how it works. So now you know the basic building blocks of automation: the senses, the brain, and the muscles. It kind of makes you think, right? If you had access to this stuff, what one thing in your life would you automate? What process would you want to take control of?